Welcome back. We've explored your journey into physical AI engineering, uncovered what the industry is really like, and heard some unforgettable stories from real world deployments. Now I'd like to make this profession feel even more real. Instead of asking the usual question, what does your day look like? I'd like you to walk us through yesterday, hour by hour. What does a typical day in the life of a physical AI startup founder actually look like?
I'd be happy to. One of the reasons I love this field is that every day combines software, hardware, artificial intelligence, robotics, and real-world problem solving. Yesterday started around 6:30 a.m. Before checking emails or messages, I opened our fleet monitoring dashboard. Our company has intelligent robots operating in manufacturing plants, warehouses, and research facilities. Every morning, I review the health of those systems. I check questions like: are all robots online? Did any embedded AI systems report unusual behavior? Are cameras, LiDAR sensors, and IMS functioning correctly? Did any robot encounter navigation errors overnight? Are battery levels within expected ranges? Did any safety alerts trigger? Fortunately, everything looked healthy. One warehouse robot reported slightly higher CPU utilization while running its perception model, so we flagged it for investigation. Small changes often become valuable early warning signs.
That's interesting. So, your day begins by monitoring deployed intelligence systems rather than immediately writing code.
Exactly, building the robot is only the beginning. Once intelligent machines are deployed, continuous monitoring becomes essential. Real world environments constantly change. Robots need to remain safe, reliable, and responsive throughout their entire operational life.
What happened after you reached the office?
Around 9 a.m., our engineering teams held a daily stand up meeting. The computer vision team discussed improvements to an object detection model. The robotics engineers reviewed navigation performance from several autonomous mobile robots. Our machine learning team shared progress on reinforcement learning experiments running in simulation. The embedded systems engineers discussed firmware updates for onboard AI computers. Meanwhile, our human robot interaction specialists demonstrated improvements to a collaborative robot interface. One thing people often underestimate is how multidisciplinary physical AI really is. Software engineers, robotics engineers, mechanical engineers, electronics engineers, AI researchers, computer vision specialists, embedded systems engineers, control systems engineers, industrial automation experts, UX designers, safety engineers. Everyone contributes different expertise to the same intelligent system.
That sounds like one of the most collaborative engineering fields.
It really is. No single engineer builds an intelligent robot alone. Physical AI succeeds because many different disciplines work together.
What happened next?
Around 10:30 a.m., I joined our simulation team. Before deploying a new navigation algorithm to physical robots, we always test it extensively inside a virtual environment. Yesterday, we evaluated how our autonomous robot behaved under different warehouse layouts. We simulated moving workers, unexpected obstacles, narrow pathways, temporary construction zones, different lighting conditions, network interruptions. Simulation allows us to expose robots to thousands of situations that would be difficult or unsafe to reproduce repeatedly in real environments. Only after passing these tests do we consider real world deployment.
So, simulation isn't simply a convenience, it's a safety tool.
Exactly. Simulation and digital twins reduce both development time and deployment risk. They allow us to experiment, learn, and improve without putting equipment or people in danger.
What happened after lunch?
Around 1:30 p.m., we visited one of our customer sites. The customer had recently expanded their production line. Because the environment had changed, our autonomous inspection robot needed an updated digital map. We collected new sensor data, verified localization accuracy, updated obstacle maps, tested computer vision under the new lighting conditions, validated emergency stop behavior, and observed how human operators interacted with the robot during normal production. One lesson we've learned is that successful deployment depends just as much on understanding people as understanding technology.
That connects nicely with human robot interaction.
Absolutely. The best robot isn't simply intelligent, it's understandable. People should feel confident working alongside it. Operators need to predict how the robot will behave. The robot should communicate clearly through displays, sounds, lighting, or movement. Trust is built through predictable behavior.
How much of your day actually involves programming?
Quite a bit. Yesterday, I reviewed Python code for our perception pipeline. Later, I optimized a C++ module responsible for sensor fusion. Then I helped review embedded AI deployment scripts running on edge devices inside our robots. Physical AI engineers rarely work with only one programming language or one technology. We move continuously between algorithms, robotics, software, embedded systems, AI models, and deployment infrastructure.
You mentioned embedded AI several times today. Why is it becoming so important?
Because many robotic decisions must happen immediately. Imagine a collaborative robot detecting a person's hand entering its workspace. Waiting for cloud processing would introduce unnecessary delay. Instead, AI models run directly on embedded processors installed inside the robot. Those onboard systems process sensor data within milliseconds. The cloud still plays an important role. It stores historical information, coordinates fleets, updates AI models, and supports analytics. But immediate decisions belong at the edge.
What happened later in the afternoon?
Around 4 p.m., our safety engineering team performed validation tests before approving a software update. We intentionally created challenging situations, unexpected obstacles, sensor failures, camera occlusions, communication interruptions, emergency stop events. We wanted to verify that the robot behaved safely under every condition. One of the biggest responsibilities in physical AI isn't making robots smarter, it's making them trustworthy. Safety validation is something we never compromise.
That sounds much more rigorous than ordinary software testing.
It is. Software bugs can usually be corrected with updates. Physical AI systems interact with people and physical equipment. That raises the importance of testing dramatically. Reliability, safety, and predictability become engineering priorities.
As the founder of a startup, I imagine your day isn't entirely technical.
You're absolutely right. Around 5:30 p.m., I met with a potential customer. Interestingly, they didn't ask, which AI model are you using? Instead, they asked, can the robot reduce production downtime? How quickly can it adapt to layout changes? How safe is it around human workers? Can it integrate with our existing industrial systems? How easy is it to maintain? Customers don't buy artificial intelligence. They invest in better productivity, higher quality, improved safety, and measurable business outcomes. Technology simply enables those goals.
That's a valuable perspective. Engineering exists to solve real problems.
Exactly. Every sensor, every reinforcement learning algorithm, every computer vision model, every digital twin, every embedded AI processor exists because it helps solve a practical challenge in the real world.
Before we conclude today's discussion, what part of your work gives you the greatest satisfaction?
Watching intelligent machines solve meaningful problems, seeing a robot safely assist workers, Watching an autonomous vehicle navigate confidently, observing AI identify product defects before customers ever see them, helping farmers improve crop monitoring, supporting doctors with intelligent medical systems. Those moments remind us that physical AI isn't about replacing people, it's about extending human capability, helping people work more safely, efficiently, and effectively. That's what makes this profession so rewarding.
That's a wonderful way to conclude today's conversation. We've learned that the life of a physical AI engineer extends far beyond programming. It's about combining robotics, artificial intelligence, embedded systems, simulation, safety engineering, and human centered design to build intelligent systems that interact confidently with the physical world. In our next segment, we'll look toward the future. How will physical AI transform manufacturing, logistics, healthcare, agriculture, and autonomous mobility? What new careers will emerge? How will AI reshape robotics? And where are the biggest opportunities for startups and innovation? Stay with us for part 5.